It's not scientifically like exact because there was a lot of factors going on there. But when I pushed my arms out, it increased the inertia of my entire body, and therefore it was harder to maintain rotational speed in that regard. So I call that a win. What do you guys think? Thank you for your help.
You're welcome.
Ladies and gentlemen, my beautiful bride.
Here.
Hi, and welcome to this week's lab walkthrough. We're going to be going into Moment of Inertia, this very bulky word that describes something, inertia, around something, rotating. And so we're going to dive into that as this lab experiment goes. But before we get into that, let's talk about this week's pre-lab activity. For this week's pre-lab, you're going to be trying to, again, get a feel for, in the real world, moment of inertia showing up and having a place in the world around you. Moment of inertia is a quality of materials that are bulky and rigid, that are not like point masses that we've been spending the entire semester studying. And the further a mass is from the point of rotation, the more resistance to change in motion that it gets. You can kind of tie this back to centripetal force. When you have something on a merry-go-round, things that are further out are having to go at a higher acceleration in order to maintain that same centripetal force, and so there's more resistance to that object rotating. But for the purposes of your pre-lab, take an object that has a particular mass and just kind of hold it at a location. I'm going to probably go shoulder level here and just kind of give it a rotate. Probably doesn't seem that challenging, especially if you're using like hand weights or kettlebell or some other kind of, maybe gallon of milk also could work, or gallon of juice. And then hold the object further away from you and try and give it a pull one way or another. And what again you're looking for is it more challenging to get it to start moving? Again, we got to overcome the sense of it being heavy and just focus on, is it fairly easy or harder by comparison to when you have it closer to your person, when you are going in that same type of motion. You should be able to detect some change, especially the heavier they are. Once you've completed that, you can answer the questions on the pre-lab sheet and then submit that, and you're good to go. And that's it for the pre-lab this week. You may recall from a previous walkthrough video, when I was talking about the theory, we talked about force acting at a distance from some point of rotation. That force caused some kind of a torque. And we talked about the development of the concept of torque, force acting on an object about some position that's away from the point about which it's going to rotate. And so we took Newton's second law and we modified the left-hand side with R times F. We defined this idea of torque that causes the force to accelerate around a circular pathway. And on the right-hand side, we had mr, the acceleration caused by the force. Remember, this is something I said we'd come back to, and here we are. We're now back to it. So, time to do this side. Here's our diagram here. We've got this massless rod, and the mass is concentrated here where the force is acting on it. It's going to cause it to follow some acceleration in this direction, both a linear instantaneous acceleration at that point and an angular acceleration that will follow along the course of the circular pathway. And that pathway is described by this radius far from the point of the center of the rotation to the mass that's actually doing the rotating. We're treating this block, this rigid body, as a point mass. And so the question is, well, what do we do with that? It gets a little sketchy to try and talk about linear concepts and angular concepts at the same time. You want to really focus that when it's necessary. More often than not, you're going to want to either talk about the linear components of what you're examining or the angular components of that same item, but you rarely want to do both. So we've got ourselves on the left-hand side of the torque here. So we've got something on the left-hand side of this formula here, the torque. That's an angular quantity. That's a force acting on a radius causing a circular pathway to be followed. But on the right-hand side, we've got a linear idea, this guy with the acceleration. So if we reach back into our bag of physics tricks and recall that tangential acceleration is defined as radius times angular acceleration, A equals r alpha. That originates from S equals r theta, the arc length. Then we can substitute that tangential acceleration out, replace it with r alpha, and as you see I've done here, and simplify everything. Torque is equal to mass times radius squared times alpha. What is this mr squared? We'll get to that in a second, but at least we've got a torque angular on the left hand side, we got acceleration angular on the right hand side, so we're kind of in a new space here, but somehow familiar. So we have this mr squared. What is that? Well, let's do what we've done all semester, which is to give it a new name. Let's define it as this moment of inertia. We'll use the letter I because moment of inertia starts with an I, and it's kind of like inertia, but you know, location, 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 right? So where the particle is relative to the axis that it's going to rotate around, it's what matters. That's what makes us. So this is where we come into this idea that the further out something is, the more effort it takes to try and get it to accelerate. Well, that's because of the fact that the further away it is, you have to do more effort to get it to follow a circular pathway. Therefore, moment of inertia, weird name, but has to do with the general idea of inertia that we saw for Newton's first law anyways, which was mass. Now it's mass at a position relative to the axis of rotation. Substitute this new definition in, and we have Newton's second law for a rotating object. Torque, its moment of inertia, takes into account this is a bulky body. It's not just a point mass anymore. It's a bulky body that has influence on how hard it is to get it to rotate. And you have your angular acceleration. That is your measure of its change in angular motion. So we've defined this item, moment of inertia, for a point mass. Remember, that's what we are doing secretly over in our previous steps, is that we're dealing with it as a point mass out rotating around an axis that's far away from the body. And in that case, so this is the moment of inertia of a point mass going at that distance. So the question is, what is the moment of inertia for, say, if an axis is traveling through an object that's in rotation? So for example, we have here on this, we have this mass that can rotate around the center of this flat side for this disk. If it was a ball, it would just rotate around this axis that's running through it. But it doesn't have to be the only thing. It can rotate around a point. In fact, a great deal of motion can actually be broken down to some form of rotation around a set axis passing through an object and some distance between that axis and the second axis. It gets real complicated. We're not going to dive into that. I just wanted to point out to you that we can take a lot of complex motion and break it down into smaller components of motion that we can manage, and a lot of times deal with where the axis is passing through the center of the mass and accomplish a real deep understanding of complex motion just based off of taking apart these little bits in that way. So here we have this moment of inertia, which will be defined. We're going to add up all the little mass pieces that are some distance away from the object, and that distance is the r squared. And I've indicated that the little ith piece, the I, J, K, L, M, just counting those using the index I. And so this disk that I just had up here, this disk is made up of little pieces that are all spread out, and they all have different radii from the center of the rotational axis. And so here's an example of a piece right here. That's the 10,000th piece, if you will. This is the 150th piece over here, and so on and so forth. We add those all up, and collectively we get the moment of inertia for this entire disk, and that will be what it takes to get it to change its motion when we put it into Newton's second law over here. And so when we take into account this sum of all the moment of inertia from all the little bits, we get a few different configurations. There's a lot of different configurations that can show up. One is a point mass. We already saw that. It's mr squared. What about a solid rod? Well, if it's a length L, let's say the length L of that rod, the distance from one end to the other, then as it works out mathematically, the rod is going to be 1/12 of mass times the length squared, not the radius squared. You can do this with the radius squared. You just get, I think it's like 1/3 mr squared, but you get the change. This This has just been simplified to use a simple measurement, which is from one end to the other. What about a disc that rotates around its flat surface? There's a perpendicular axis that's passing through here. We'll refer to this as the flat surface, and this perpendicular axis is going to rotate around that. It's going to have a certain moment of inertia that's going to be given by 1/2 mr squared. And if we instead are going to rotate it around, and if this mass rotates around an axis that's vertical, passing through the diameter, the full length of this, and passing through the center as well, all the way through, then this is going to rotate like so, and the moment of inertia of that is calculated to be 1/2 of that from the flat rotation. In this case, we'll refer to that as the edge rotation, and that's going to be 1/4 mr squared, or 1/2 of the flat disk moment of inertia, and we're going to measure that experimentally in this lab. So how's it going to work out in the experiment? Well, you have a spreadsheet that has that has been worked up so that you can punch your values in and make observations in the course of doing the experiment. And the way that theoretically works is as follows. So here we have a top view of the object rotating. In the example here, I've got the rotating arm, but it's going to be the same physics regardless of what's being rotated, whether it's just the core or if it's the armature or any of your discs in configuration. But you have one of the spools of the radius that you know, the spool radius that you know, and a tension that's caused by a string that's wrapped around the spool, and that's causing the acceleration at that point, a tangential acceleration that corresponds to the angular acceleration that the apparatus is experiencing. And then over at the smart pulley, we have the string going over top, and it's causing the which is being pulled by the hanging mass and accelerating downward. Now, at the spool, we have the torque acting on the armature to cause it to rotate, and we have radius force that's acting and sine theta. We're going to assume 90 degrees, but you may want to take into consideration, especially if you see high errors, whether or not your smart pulley was actually lined up with the edge of the spool in the way as described in the lab manual. In other words, did you have actual 90 degrees of that torque acting on that at the point of contact on the spool? Well, we substitute the assumptions in, and we have a torque, radius, and the tension that's acting. And remember that torque is, by definition, moment of inertia times angular acceleration. And so we have this, that's our first equation. Then we look at the free body diagram for the hanging mass as it's accelerating. Remember, we have F equals ma. In this case, it's a tangential acceleration that's doing this. As I prefer to do when I go to a Newton's law equation is I'm looking where the acceleration is, and then I'm making that the positive direction. So the force that's acting in the direction of the acceleration is the positive mhg. That's the hanging mass under the acceleration due to gravity, minus the tension that is acting as a resistance force in addition to the mass. And then that's going to be equal to the hanging mass and the acceleration it actually experiences as it accelerates towards the ground. Rearrange this, we get tension on one side, everything else on the right hand side looks like so. And this is our second equation. We can substitute this equation back into our equation number one, and we have moment of inertia, angular acceleration, the hanging mass, and all this stuff on the right hand side. Now we have a bit of a quandary. Remember, it's very headache inducing to deal with angular quantities while dealing also with linear quantities. So we're going to choose one of these two to go. Could we go one way? Is one way better than the other? Depends on your experimental apparatus, really. With the equipment that we have on hand, we find that we're getting better results when we use the smart pulley in the way that it is. So we'll go the direction of the tangential acceleration that's causing the pulley to accelerate, and we'll make substitutions in that way using A tan, again, is equal to R alpha, or you invert that alpha substituted in this place, gives you A tan. And this leads to your expression that's seen in the lab manual, looks like this guy here. So this is how we're going to measure. You punch in the angular acceleration, the hanging mass, and the radius of the spool, and this will give you your experimental moment of inertia for every calculation in the spreadsheet. And then that will be compared to the theoretical values that you have here once you subtracted away the core moment of inertia that you did experimentally. That's for part A. In this lab activity, you'll be working with multiple different components of a single device. It's similar in complexity to the centripetal force experiment in that we're using the same base that we use in that lab. Only now we're going to pay some attention to different components of it, namely the spools that you see here. There are 3 spools around which the string can be tied, and this will be the string that causes it to begin to rotate, which is what we're going to need in order to make our measurements. This assembly here we'll refer to as the core, and there are 3 spools here, small, medium, and large, that you'll want to measure the diameter of each of these and put those into your spreadsheet as you do your calculations. Make sure that when you make the measurements you are paying attention to the diameter of the barrels, not the flanges. You want the barrel diameters, and then the spreadsheet should calculate the radii based off of those measurements. You can use the vernier calipers to make those measurements. One of the components that you'll be measuring the rotational motion of is this platform. For the purposes of the experiment, we are referring to this as a platform rod, or just a rod, because of its high aspect ratio of its length and its very narrow features by comparison, and it's going to go around in a rotational, around an axis about the center of the mass, and you'll have those calculations available to you in the spreadsheet, and also the formulas are found in your lab manual. But this has on it a mounting block which will be detached in a lot of cases so that you can measure this because of this screw and its size and other justifications. You'll take one and place it on the assembly, taking care to loosen up and then fit it in place so that this whole assembly becomes your core for the initial part. This is a nice geometric shape, however it's very small and contributes a very small amount, but a measurable amount of moment of inertia to the assembly. And so to obtain the best results, you'll be making a measurement of this mass and the lengths, the side length of this block. Now this block is referred to as the core block. It's got the rotating platform. It's also the mounting block, as you might find in the lab manual. The mass that you'll be rotating as a point mass will be this block mass, this square block mass, and you can tell they're very distinctly different items, and we'll discuss this in a moment. But you'll place this initially on here. You'll make your initial moments of inertia measurements of the core with this as it begins to accelerate under the force of the pull from the string over the pulley. Notice that for the small spool, this becomes a very large percentage of the radius, and it's not very negligible and can affect the actual diameter and therefore your calculations, assuming the torque that's done in the theory. So we want to avoid using the small spool in the course of this experiment. Even the medium can be a little bit challenging, and the large can give you the best results, the least amount of change of the diameter, so the slope is got the smoothest, straightest value. So use the medium or the large, but do not use, when you're making your measurements, do not use the small. It's just too much error comes into that problem. Once you've done the measurements for the core moment of inertia, you take this off, remount it onto the moment arm, platform arm, and then you place this as such. Make sure that you tighten the screw on this, because if you don't, there will be give and inconsistency in the results. You want to tighten that up nice once you have it in place, and that's seated as full down as you can. You'll then take your square block and want to mount that on there. Now there's a correct and an incorrect way to mount this block, and you can tell with these 2 ridges on the bottom, these are supposed to fit into the track. So this hole should be aligned with the track here. If it's not, you may be inspired to try and place it on the track like so. However, the problem is that even with this alignment, you're still estimating where the center of mass of the block is. It's better to use more reliable points. So you turn this so that it's seated inside, it's either facing this way, either way, and then you tighten it up accordingly. But wherever you tighten it, you can use the inner radius from 0 to the inner edge of this, and then the outer radius, which is the distance to the outside point. And this will give you, the average of those distances will give you your center of mass. This is already set up in the calculations in the spreadsheet, so really just want to make sure you understand that this is the inner radius and the outer radius compared to the axis of rotation. You also want to make sure that you get the length of this measured. Avoid having your square block too close to the center, because the smaller the radius, the lower the moment of inertia. We really want to have this moment of inertia distinguished above the noise of error, so the further out you go, the better you're going to get some results. Try not to go too far out though. For part C, you'll have this disc in place that you can set into place on your object. Once it's fully seated, this is very well balanced, and you can put quite a bit of mass on here and rotate it using the string attached to your hanging mass. A bit trickier in this example though, you'll notice that on either side there is a block, or there's a hole on both sides. You can choose either one and place it. Try and align the screw to be on the flat edge of the rod. Because of the potential stability issues with this configuration, you definitely want to wait until you have a TA come tighten this up for you. So when you get to this point, make sure you alert your TA and they can come over and tighten this up to prevent significant shifting. It can be eliminated once this has been tightened in place. And then of course the hanging mass can be put on there. Again, you don't want to go too high, as high as you can go with the flat disc. This is the edge disc on the edge. You don't want to go quite as high with that because of the fact that it can have instability and potentially fly off, especially if it was not tightened properly before beginning that experimental part measurement. Your goal here is to make sure that the measurements are comparing out to the theory with good percent difference. All right. This is the secret code word of the day. For the first time ever, going with a code word so that I know who's paying attention to the videos. I can see who's looking at the videos, but I want to know who's paying attention to the details. If you tell me Rumpelstiltskin, don't tell everybody, just say Dr. Tracy Rumpelstiltskin, I will know that you were paying attention to this detail in the walkthrough. And that is this. There are two masses at your station, and that's intentional so that you can choose the best masses that you like to use in order to make your measurements and accelerations. So you have the masses that have these large clumpy amounts, and then you have your hanging masses that you are familiar with these 5-gram hangers plus the individual masses. Now remember, you'll note that in the lab manual there is the range goes up to like 305 and so forth, and the reason is because of the 5 grams. You can put 3 100s on here. Just make sure you always drop your masses into a safe catching box and avoid allowing the speed to go too high. If you get your armature set up before you get started, set this up just like this and take a few moments, and you will be able to determine whether or not this is balanced. This is not balanced because of the configuration I've set up here for video purposes. But this is an indication that it's not balanced, and it needs to be balanced in order to get your best results. Otherwise you're going to have big wobbles in your data, and you don't want to have that. So make sure that you're observant of this. It takes a few moments to do this. You can do this while I'm up at the front blathering about physics and stuff, and you can just kind of get your initial sense of that. And if you do need it, you can just flag down one of the LAs, the assistants, and then come and balance out while I am going on and on. So once you know that this is balanced, you take the core block. That's a small block. That's actually a mounting block for the bottom of the aluminum platform rod, and you set that on there. Just set it on there, screws facing down, and shift it around until the screw seats into the space once it's in place, and then tighten it so that there's no wiggle space. This is pretty much ready to go once you've made sure that the windings are snug against there. Now remember, you don't want to do any of your measurements with the small spool, because that is very problematic, because the radius is very susceptible to the layering of the string on this. So medium, large preferably, run that over top of there. And the moment of inertia for this is very small, so using a large mass is not going to be a great idea. You can start at 50 grams and put that on there. Begin. Have it ready to go. Remember, you don't need to synchronize your timers. Just start the timer start the data collection and give it a few moments. Once it's been in place, this is triggered by the spokes on the wheel passing through the beam on this, and so you don't need to try and like synchronize it well. Give it time to get started taking data, and then simply release it, allow it to fall freely, and then just make sure that you rewind it before your next run. You'll do that for a range going higher masses in the range explained in the lab manual, and then make sure you get 6 configurations with different settings for the hanging mass, and maybe do a couple of each, the middle and the large. And that'll be part A. You'll know the moment of inertia of your core assembly. Then for part B, you'll have this in place. Remember, if you don't, there's a lot of play that happens here if you don't tighten this up, so you want to make sure that that's snug to get the best results. And now there's no play. You don't want the square mass block too close to the center, because then it's no longer a point mass acting at a radius, it's actually a bulky body rotating around, and axis is passing through that body. So you want to make sure that that's some good distance, a minimum of no closer than 5 centimeters, but I would really kind of go a little bit further out for your measurements. Get into the notch. I'm going to go down to the large. In this case, run it over top like so. In this case, it's currently aligned with the middle. So once it's up here, you can adjust this so that the string goes over top of the armature. Tighten that back in place. It will shift in place, so you want to be a little bit diligent with it. But once it's locked in place, then starting with say 150 grams or 200 grams, put that in place, begin the data collection. Again, no need, just make sure it's not swaying too much. I know you can't see it off camera, but there it is. And then it'll begin to rotate as such. We're going to stop that. When you finish with this, remove the armature, place your disc right in place on top. This will fall right into its notch location, and then you just repeat the process, but this time for 3 runs of this at preferably at the large radius, and you can go as high as 500 grams. I'm not going to demonstrate that here, but the idea is pretty straightforward. And then once you've got your 3 from that one, you gently remove this and place one of these in like so, and then ask for a TA to tighten it up. And once it's in place and it's safe to rotate, once again allow it to get started data collecting, and then you can release it and let it accelerate. You notice it's accelerating pretty good, and that's just with 200 grams, so you don't want to go too high with this one, at least not without monitoring it closely. It can go faster, but you want to practice safety in the laboratory with this equipment. Again, go to the hardware setup, click on the first one. Again, we're using a photo gate with pulley, so we're going to click on that, and it's going to come in. We're going to want a graph, so we'll bring a graph onto the table. Close the hardware setup. Set it up for linear speed. It should automatically bring up versus time. And then remember, once the data comes in, it's going to be very flat. You're going to be surprised. It'll seem like for a bit you might not actually be getting any data, but you actually are. This very slow acceleration for this. When you're measuring the moment of inertia for the apparatus alone, make sure that you use masses that are minimum 50 grams. Otherwise, you start seeing some friction effects that come in there, and they can make your determinations a little unfriendly. So you come in here, and you click on Expand. And now you can see there's a little bit of wobble. Apparently the hanger was wobbling in the process. We'll do the same thing we ordinarily do. We grab a highlighter box, expand it to capture the amount of data that we want to fit, go into our linear weight because we're looking for that nice straight line for velocity versus time or speed versus time. That'll give us our acceleration. And we see that the mass, or the slope, we see that the slope is 0.0171. That is your pre-experimental moment of inertia. And then
capture as many as you need, usually about 6 data points for the core. Then you'll repeat for 6 data points for the rod and block. And then 3 captures each for the disk flat and the disk on edge. And that's it. Then you analyze the data.
Well, that does it for this week's walkthrough. If you have any questions, of course, this is a fairly new version of the lab activity, and so please make sure that if you spot any inconsistencies in the lab manual or in the spreadsheet to reach out, let me know, or let your TA know so they can let me know. And other than that, we'll see you in the lab. All right, let's see if I can just spin out of here. See y'all there. Hi there, and welcome to...
Fine, I'll make it stop.
Domo arigato. At least not while I'm recording. I guess that worked. You may recall in a recent conversation, you may recall from a this little bit right here is for the math nerds. I didn't really need to say that. It says so right here. It's for the math folks. Okay. That's all I got. Oh, did I do an outro? I guess I didn't.